Hi and welcome to the second clip in this series on AS and subsequently A2 chemical kinetics. In this clip we're going to start with the previous diagram that we had, which was a Maxwell Boltzmann distribution of a graph at a specific temperature. That temperature is not necessarily known, but we will say it's at 290 degrees. So the initial curve is at 298 Kelvin, let's say, as a random number. So this is curve number one. This, as we said in the previous clip, is demonstrating that at a specific point whereby we have the activation energy, this number of particles are sufficient to have the activation energy and will subsequently react. That will give rise to a specific rate of reaction that we could measure. Now what we're going to now do is change the temperature of this reaction, and we'll increase it by, let's say, 20 degrees, and we'll go up to 318 Kelvin, and this will increase the temperature of the reaction. This will increase the average energy of the particles. So all of those particles are going to start to move faster, they'll start to vibrate more around, and they'll start to have a more energetic state. What is key to this is the number of particles is not changing. Now, if you remember the previous clip, what we said was the area under the curve, i.e. all of this area, including those higher than the activation energy, represents the total number of particles in the system. And so if we are not going to change the number of particles and all we're going to do is change the temperature of the reaction, that area under the curve cannot change. And so if we increase the temperature, the most likely energy that a particle is going to have is going to increase. So the peak of the new curve is going to move towards the right. It's going to increase in its energy. So the average energy of the particles, the most likely energy of those particles, is going to increase. If you imagine that it has to start at the origin, because again we have zero particles with zero energy, then it's likely that the curve is going to head off towards that right hand side of the original curve, because more particles have got higher energy, and therefore it's less likely that particles will have a lower energy. So the curve will appear to be lower than the previous one. The maximum energy is then going to proceed towards the right hand side, showing that the most likely energy of a particle in a bulk collection of particles is going to be larger. Now if you imagine that we'd drawn this out as a piece of string, in order to keep the area underneath the curve the same, the height of that peak will have to go down. So not only will it go towards the right hand side, demonstrating that it's got an increased energy, the peak will also decrease slightly. This, hopefully you can see then on this diagram, that the area underneath the blue curve is approximately the same as the area under the black curve. And what you can therefore see as well is that because the activation energy has remained the same, we haven't added a catalyst, then what we've now done is significantly increased the number of particles that now have the desired activation energy. And what you will see in an observational point of view is that a temperature rise to a reaction can have quite a marked effect upon the rate. And this is why when we do discussions of these, we see that only a 10-degree rise leads to quite substantial, approximately double, increases in the rate of the reaction. Here we've increased it by 20 degrees, but we were using generic diagrams. But you can see that the area under that curve towards the right-hand side of that reaction has now significantly increased. And when you get to questions based on this, you are now looking at many more particles having the desired activation energy. And this is quite often a key to a past paper, whereby you have to specify that it's many more particles having the activation energy for a reaction. And so what you see is a large increase in rate. Rather than if you just simply double concentration or you double pressure, then you get a doubling of the rate of reaction for a first order reaction. But for temperature, a relatively small increase in temperature, so 10 degrees, 20 degrees, leads rise to many, many more particles having the activation energy, leading you to large rate of reaction increases. And so you see a more marked effect on rate of reaction when you have a temperature discussion. In the next one, we will have a look at how concentration changes, that and pressure being an analogous discussion, but how concentration affects the position of a Maxwell-Boltzmann distribution and how that subsequently affects a rate of reaction. So thank you very much, and I will again see you in the next clip.